Thank you. Good afternoon. My name is Dieter Spar. I'm a self-employed software developer, and one of my so-called hobby projects is playing with GSM. I want to talk today about the following things. I want to tell you about the motivation for why to play with GSM. I'm going to introduce a few GSM-related projects. I want to present a few thoughts about an open phone. I will give you an example of how the hardware of a phone can be used to sniff the air traffic. The main part of this talk is about a denial of service attack to the GSM network with a phone and a modified firmware. And hopefully I can also give a demonstration of this denial of service attack. I found out that we have some bad coverage of our own network, and of course we don't want to demonstrate this denial of service attack to the official providers. So, why to play with GSM? The GSM system is there for quite a long time. In Germany it was introduced 1992. However, the protocols and the system is not very well researched compared to TCP/IP. For TCP/IP, it's really simple. You just need a few PCs, a network card, and you can start to play. You find everything what you need. Client and server applications, the source code of the TCP/IP stack, everything is there. For GSM, it's very difficult. You don't have usually access to the network. If you're not a provider, you don't know what's going on inside the network. And even if you have cheap phones available, you usually don't know what is going on inside the phone. The situation has changed a little bit in the last years. On eBay you can find used GSM equipment. It's not very expensive and you can buy it. There are several projects which take care about GSM. OpenBTS, OpenBSC and AirProp. I will introduce them right now. You find also all the specification for GSM. However, the specification is really huge, about 2,000 documents, some of them with several hundred pages, and not written in a way that it's easy to understand. So if you want to start understanding GSM, take the specification as a reference only and buy a good book and learn it from there. Before we continue, I want to introduce just a few abbreviations we need during this talk. The phone in GSM terms is called MS, or mobile station. The BTS, the base transceiver station, is what you actually see from the GSM network. Those are the antennas on the buildings and on the masts. Behind that is the BSC, or base station controller, which controls the base transceiver stations. And behind that is the mobile switching center, which is there for routing the calls inside the network or to the landlines. The interface between the mobile station and the base transceiver station is called UM, or air interface, and the interface between the base transceiver station and the base station controller is called ABIS. This is enough for what we need for our talk. The other parts of this drawing are not that important. And just as a notice, this is only the part for voice traffic. For data traffic, GPRS, Edge, you have additional elements which I have not shown in this drawing. So now to this project which take care about GSM. The first is OpenBTS. As the name implies, it's about building your own base transceiver station. The hardware used by OpenBTS is the USRP, Universal Software Radio Peripheral. Probably some of you already know it. It's open hardware which can be used to receive and transmit on a rather wide range of the RF spectrum, down from DC up to several gigahertz. It all depends on the card you plug into the USRP. OpenBTS implements its air interface as a software-defined radio. This means that all the signal processing stuff is running on the PC. And OpenBTS does not follow this classic model of the GSM architecture with BSC, MSC and all that. It uses a direct to SIP approach. For this, it uses asterisks, and it can do voice over IP traffic and conversations. The second project is OpenBSC. As the name implies again, it's about building the base station controller. OpenBSC implements the ABIS protocol and some parts of BSC, of course, the mobile switching center and the home location register. The OpenBSC supports currently two types of BTS. The first is the Siemens BS11 micro BTS. It's a GSM 900 unit with a maximum of 2 watt output power. This can be reduced down to 30 milliwatt, which is quite nice for testing. The unit is about 10 years old, rather cheap, and even with the name micro BTS, it's a quite heavy unit, 30 to 40 kilograms, depending on the configuration. Configuration means the number of transceivers which are built in. You have a unit with one transceiver or with second transceivers, with two transceivers. The ABIS interface is implemented as an E1 interface. So this is basically ISDN primary multiplex. So you need an E1 card for your PC2 if you want to talk to the BS11. The second BTS supported by OpenBSC is the Nano BTS from IP Access. This unit is a device currently sold, so it's available for various bands. The maximum output power of the 1800 megahertz unit is 200 milliwatt. As you can see from this rather low output power, this device is intended for example, indoor installations where there is no coverage or for ships and planes. The device is rather small. It's also available with GPRS edge support. And one big advantage is that the ABIS protocol is run over IP. So you just plug it into your standard network equipment and you can use it with OpenBSC. OpenBSC and the Nano BTS is also used here to run the GSM network of the Congress. We have 4 Nano BTS units installed and they're spread here over the buildings, and yeah, they give you the access to GSM and the internal DEC network, and you can also make calls to the outside. Here's a picture which shows the Nano BTS and the BS11, just to get an impression of the size. Those 3 small wings in the edges of the Nano BTS are the antenna of the Nano BTS, and the black box in front of the BS11 is the antenna for this unit. Of course, for 2 watt and for larger range, you need bigger antennas. The last project I want to introduce is AirProbe. AirProbe is about passively sniffing the GSM air traffic. It's also based on the USRP and GNU Radio. And one of the goals of AirProbe is to analyze the protocol and display them with Wireshark. Wireshark can actually display quite a lot of the GSM protocols already. And AirProbe can also be used to capture the traffic for FF1 GSM encryption. There was a talk from Carsten Nohl and Gus Patchett on the first day, and you probably have all heard of it already. So what about an open phone? Actually, there is no real open phone project there right now. A few years ago, there was Project Blacksphere for the old Nokia DCT-3 phones. It was about reverse engineering the firmware of the phone. And I think one of the things which were achieved is to write some sort of operating system which can be loaded into the Nokia phone. However, this operating system does not support the RF hardware, so you cannot send or receive anything with it. It's just for, I think it was for demonstration that you can load your own games or applications inside the phone and run them. And to my knowledge, Project Blacksphere is no longer active. Then there is the TSM30. It's an old phone based on the Calypso chipset from Texas Instruments. The source code for this phone can be found on the internet. And with this phone, you can try several approaches. I tried the following. I tried to control the complete hardware on my own. And as an example, the phone can be used to sniff the air traffic, similar to the USRP, however, with some drawbacks. I will go into the details later. The second approach is to use this firmware as it is and make some modifications or try to see what can be done with it. The example is the denial of service attack, which I also will present later. And just for your information, the OpenMoko phones also contain a GSM modem with the Texas Instruments Calypso chipset. However, the version of this chipset is a little bit different, and there's also a different RF transceiver chip inside this GSM modem. So you cannot simply take the source code of the TSM30 and run it on the OpenMoko GSM modem. And one thing to note at this point, even if we have open source, so-called open source phones, the Freerunner, the OpenMoko Freerunner, the Android phones, this does not mean that there is source code for the GSM modem available. Basically, those smartphones are really two different application processors inside, two different processors inside. One is the application processor, which runs the open source software, Linux, and the user interface. And then there is the more or less closed baseband processor, which does all the GSM stuff. So even for an open source phone, you usually don't have access to anything inside the GSM modem. A future plan, just some ideas which might be, which we might look at in the next 1 or 2 years. It's probably not an easy project, is to take a GSM RF transceiver and a baseband chip, connect it to a cheap DSP FPGA board, and develop true open software on it, which at some point might be used for sending and receiving like a phone. The advantage of this approach is that it's probably cheaper than the USRP. Not sure yet how much, but probably more or less half the price, maybe even less. And a lot of the processing power, which is currently done in the PC, if you use the USRP, will be transferred to this DSP FPGA board. So you don't need a powerful PC to run such a setup. A few more details about the TSM30. This phone is a Spanish phone. It was also distributed in Mexico and Chile. You sometimes find it on eBay, especially eBay Spain. I think it's also available on eBay Mexico sometimes. The phone is about 6 years old. It has GSM, GPRS, WAP support. This Texas Instruments Calypso chipset consists of 3 chips. We have the RF transceiver, we have a digital baseband chip, and we have the microcontroller. The microcontroller actually has 2 cores, an ARM and a DSP core. And for the microcontroller, you can also find a few leaked documents on the internet. Just to give you an impression of the source code for this phone, which can also be found, it's written in C. The whole source code, which runs on the Calypso ARM core, is about 2.5 million lines of code. From this part, the GSM protocol stack, GSM and GPS protocol stack actually is 400,000 lines of code. Layer 1 is 130,000 lines of code. Layer 1 means this is the part which actually controls the RF hardware of the phone. It does not include this source code for the DSP. Actually, the DSP gets its code from ROM, and there is no source code for this DSP, and also no information available. Basically, the DSP does all the signal processing which is required to receive GSM. There's also a second microcontroller inside the phone. It's not used for GSM stuff. It controls the camera of the phone, or it takes care of the micro SD slot. This second microcontroller, the code for it is about 350,000 lines of code. So what can you do with such a phone if you control it completely? For example, you can sniff the air traffic. A very simplified diagram of the Calypso chipset looks like that. You have the antenna, you have the RF transceiver, which brings down the GSM frequency to some intermediate frequency. You have the baseband chip with an analog to digital converter. There's also a digital to analog converter and a modulator. This is needed for sending. And you get a digital data stream, which is transferred to the microcontroller with the ARM and DSP core. So if you want to sniff the air, you basically tune the RF transceiver to the GSM channel you want to receive. You tell the ADC to start converting the samples, and you get a digital data stream with about 271 kilosamples per second. One sample consists of two 16-bit IQ values, so in total you have about 1 megabyte of data per second. This data can be used with GSM receiver, can be used and decoded with GSM receiver from AirProbe. However, there is one big problem, how to bring out all this data from the microcontroller. The Calypso microcontroller only has a UART connection, no Ethernet, no USB, and the UART connection is too small. For a proof of concept, I just sampled 1 second inside the internal RAM of the phone. It has about 1 megabyte, and tried to decode it with a GSM receiver. This basically works, but it's not yet useful to decode, of course, a lot of a whole conversation or something like that. Future plan is to make use of the DSP inside the microcontroller and put some of the processing work, which is currently done by GSM receiver, inside the DSP. This way it might be possible to bring down the samples, let's say, down to only 271 kilobits per second, which can be transferred with an UART, no problem at that point. The UART supports this speed. The problem is there is not that much space in the DSP. It might be possible with some optimized assembler, but it has not been done yet. But basically, yes, I hope it's possible. So the second thing you can do with the phone is just take the source code as it is, have a look at it, try to understand it, and see what else can be done with it. One of the things is to implement a denial of service attack. I will give some overview of this attack. The theory for it is known for quite some time. I think 2 or 3 years ago, the first time some information was published that this denial of service attack is possible. However, to my knowledge, no one has demonstrated this yet, and of course there is also no implementation in a phone, at least to my knowledge. The attack itself is possible because of the way an idle phone works and has to access the GSM network. The details will follow later. So because this attack is basically inherent to the system, there is no way how to fix it. You cannot simply change the whole GSM system to make this DOS attack impossible. The attack itself affects only one cell. It does not affect the whole network. So it affects this cell where the phone sends its information to, but not the other cells. The attack happens at a very early stage. No authentication of the phone has been done yet, so even a phone without a SIM card can be used. Additionally, no information of the phone has been transferred to the network, so it's a totally anonymous attack. And there's also not much which can be done against it. Someone can try to locate the attacking phone, but this is rather hard due to the way the attack works. It does not continuously send, so it's not very easy to locate the phone. To understand the details, I will go into a little bit more theory of GSM. GSM uses TDMA, time division multiple access. This means a data stream is divided into frames. Each of the frames is divided further in 8 time slots, and each user gets one of those time slots. Inside those time slots, the data is transferred with so-called bursts. The burst has a maximum length of about 160 bits. However, you cannot use the whole 160 bits as a payload. Some of the bits are for synchronization purpose. Also, you have forward error correction in GSM. So let's say only 60% of all that can be used for payload at all. There are different types of bursts. One of them is the so-called frequency correction burst. It's used to synchronize the clock of the phone to the clock of the network, so that they use the same time base. Another burst is the synchronization burst. It tells the phone about the frame number, and it's also used for synchronization purpose. A third very special burst is the so-called random access channel burst. This is the burst which is sent when the phone at the first time tries to access the network. At that time, the phone is only listening to the GSM network. It has not sent anything yet, and it does not know the distance to the base transceiver station. So what the phone does at this point is it sends its burst when it receives the start of a frame from the BTS. However, due to the propagation delay, it takes some time till the burst is received by the BTS again. So as you can see from the diagram on the upper side, the burst is actually received somewhere inside the frame. If the burst would have the full length, it would overlap with the next frame and cause distortion. So in GSM, you have the length of the random access channel burst is about half of the size of the other bursts. This length comes from the maximum distance a phone can have from the BTS. In GSM, this is about 35 kilometers. Due to this very short size, you can only transfer as a payload 8 bits. Those 8 bits are basically used to encode the reason why the phone wants to access the network. For example, it wants to register, it wants to answer and call, it wants to make a call, hand over is another reason. And you don't need all 8 bits for this. The rest is used as a random number in case when two phones send a burst at once and collision can be avoided this way because you can distinguish two bursts from different phones. So what happens inside the network if this random access channel burst is sent? This burst is called a channel request because the phone wants to get access, it requests a channel. The BTS sends a channel required message to the base station controller. The base station controller activates a channel, it waits for the acknowledge from the BTS and sends an immediate assignment to the phone through the BTS. This immediate assignment opens the channel, and a channel is established now, and a conversation between the phone and the BSC can take place. However, the channels you want to allocate are a limited resource. The BTS only has a certain number of channels. This depends on the size of the BTS. BTS with 2 transceivers typically has around 25 channels available. For a larger BTS with 4 transceivers, you have about 40 channels available. So channels are a limited resource. And one thing which happens if the channel is not established is that the base station controller releases the channel again. The timeout for this release depends on the manufacturer of the equipment. It can also be adjusted. To what I've seen so far, it's in the range of 2 seconds to 5 seconds. So if a channel is allocated, it stays allocated for 2 to 5 seconds and is then released again if no real conversation has been established. What we now do in this denial of service attack is that we simply send those channel requests but don't care about the immediate assignment. The effects of this continuously sending random access channel bursts is, first of all, we are jamming. If we are very close to the base transceiver station, closer than the other phones, and sending with a much stronger signal, the other signals of the other phones cannot come through. We simply jam it. We don't care at this point about resource allocation because we are jamming the signal anyway. The second effect is that we, of course, allocate the available channels of the BTS. So no other channels are available if another phone wants to request it and would come through. This attack does not influence existing connections. If you are making a call, this call will not be disturbed or interrupted. However, for a phone which wants to access the network the first time, for example, register, make a call, answer a call, it can be difficult or completely impossible to get access. As a result, a phone might switch to another cell at some point. It depends on the implementation of the software and the GSM stack on the phone when this happens, but it will at least try to get access to another cell. Also, with this attack, there is no 100% guarantee that the phone won't get access to a cell. So you might think about using this attack as a mechanism to block a cell. For example, if a bomb is triggered via GSM, you could use the phone to simply make it impossible that this bomb gets triggered, but it's not 100% guarantee. So for this thing, it cannot be used. Maybe it can be used if you amplify the signal of the phone to, let's say, 10 watt or more than the typical 2 watt you have with a phone, and then you are jamming the signal of all the phones for sure if you are close to the BTS, but not with the simple phone. One useful application is you can also attack an INSI catcher. An INSI catcher is in fact a false base station. It sends a stronger signal than all the other cells, the official cells, and the phone tries to register to the INSI catcher. INSI catchers can be detected. A typical sign for an INSI catcher is that encryption is turned off. So with a special firmware in your phone, it is at least imaginable that the phone detects encryption is turned off and asks the user if it wants to attack the INSI catcher. This would make the INSI catcher absolutely unusable because no other phones can get access to it anymore. This is, of course, what we want. Here in this diagram, on the first sign, it looks a bit complicated, but this diagram is the result from an experiment with the denial of service attack to a real network, however, in a controlled environment. It's not a real network in production, but it's a real network in a lab environment. A real BTS, a real base station controller, not OpenBSC, but some commercial available components. The results for this diagram were generated from a trace on the ABIS interface, the interface between the base station controller and the base transceiver station. On the lower diagram, you can see the number of random access channel bursts which were generated over time. And on the upper diagram, you can see the number of channels which are active. We have two transceiver BTS. This BTS was configured to have 24 available channels, and this is also the maximum of channels which can be activated at a certain time. What's interesting to see in this diagram was that the base station controller does not actually implement a timer for each of the channels. Instead, it seems to work this way. It periodically checks if channels have expired and then releases all of them at once. Those are the drops you see in the curve. At each drop, the base station controller has determined that several channels have expired and it releases them again. One other thing to note, at the time these measurements and tests were made, the phone was not yet able to send a rock density of 100%. In fact, it only was able to send about 20%. This means only every fifth possible slot the phone was able to send one of the bursts. Right now, the phone is able to send 100% density. This means depending on the configuration of the cell, 100 or 200 channel requests every second. So you can imagine you allocate those 24 or 40 channels really quickly. Here's another diagram. This time it was a BTS with 40x, with 4 transceivers. We have 40 available channels. The diagram is very similar. I tried to draw with the red line how it might look if we had 100% density at the time of the measurement. The number of channels would have been allocated much faster, and because there were more channels expired in the same time, also the drops would be deeper. What we can also see from the diagram is the only point in the diagram where a second phone would be able to get access is when these drops occur. In all the other places, every available channel is allocated, and no phone would be able to get access, even if we don't jam. And are, for example, far away from the base transceiver station than the phone which wants to get access. Okay, now let's see if I can give a demonstration of the denial of service attack. I want to explain what I want to try to do. We take the conference GSM network as our target, of course, no real network. It's the nano BTS, as I already mentioned, an open BSC behind. I have one phone which is doing the attack, and I have a second phone which is trying to get access. The problem, which I will have to check if it works, we have a very bad coverage here. So I hope that the two test phones still receive the conference network and not something else, but I will check that. To see what happens, here's a log of the GSM. This is the console of OpenBSC. It actually shows some events, what is going on the network, on the complete GSM network of the Congress. If someone with a registered phone, for example, would now try to send an SMS, we would see the message on the log. Maybe someone wants to try. I will now see if my phones are still working as expected. Okay, this one looks good. Okay, one problem I might have. I can most certainly demonstrate the attack, but my phones, the two phones, are registered to different cells. So the phone which wants to get access would get access, and the phone, the attacking phone, would attack the cell, a different cell. So we probably won't see that it's possible how it looks like if another phone tries to get access. But let's just start with the attack, that you can see what happens. To start the attack, I implemented it in a way I just have to dial a special number, and let's hope, yes, it's starting. I will try to make the noise of the bursts that you hear them with the interference to a radio. This is the rate, just to find, this is the rate of the bursts. Just to get an impression how it looks if a phone normally sends the bursts, I will send an SMS with this phone. Okay, we have some other interference here from the monitor, of course, and let's see. Not yet. It's trying. I think you can hear it. Those are much slower. Okay, let's try it again. Did someone notice when he tried to send an SMS that the cell he was registered to was no longer available during the attack? No? Okay, I just turned it off. Maybe some of the people who have registered phones to our network want to try it again. I can again start this attack, and it works in the background, so no problem. It's implemented in a way that it just sends for 1 minute those bursts and then it stops again. Of course, it would be possible to send for a much longer time. And as you hear from the radio, you hear those short bursts. This is what makes it so difficult that a phone can be located. You only have due to the way those bursts are sent, you only have about 10% where you send 10% of time where you really send a signal. During the other 90%, there is no signal sent from the phone. And this makes it so difficult for standard equipment to locate the phone. So if someone with just a directional antenna tries to detect you, it's usually very hard without really expensive equipment. So imagine to take this phone and walk around and see what happens. Of course, it's not recommended to do this. This is perfectly illegal. Okay, I think we have a network error, but this is the network here, so it does not care. Here are a few links to the projects I mentioned, also to the places where you can get the specification, and special thanks to Harald Welte. He's the one behind OpenBSC. Most of you probably know him, and David Burgess, he's behind OpenBTS. So, any questions? Thank you.
Please use microphones at the side. People who want to leave, please wait a few minutes. Don't make too much noise so everybody can listen to the answers. Thank you. Okay, we have one here.
Thanks. Can you quickly talk about how you implemented it? Is it true that it's just using the phone to attack?
Yes, it's the standard firmware as it comes for this phone. I searched for the location where those random access channel bursts are sent, and I implemented it in a way that they are sent continuously. There are some implementation details, especially the problem that initially only 20% of random access channel burst density could be generated. This is was a little bit deeper inside the phone, but it's really implemented with using the standard GSM firmware which comes with the phone. No modification to the hardware or setting different registers or something like that was necessary.
So what you're basically doing is like a flooding attack on all open channels. So now our phone is able to access the GSM network, right?
You mean this phone?
The phone is flooding, saying, yeah, hello, I'd like to have a connection, I'd like to have a connection,
Yes,
I'd like to have a connection.
allocating
And
all
the
the
base
time.
station or transceiver station is saying, oh yeah, you can, but the time frame between releasing and is so long that you can flood all open channels. This is a DOS attack basically, right?
Yes, you allocate the resources, the channels, and the other effect, of course, is this jamming effect. Usually in a cell, the cell tells the phones how much power it should use to send those initial random access channel bursts.
Yeah.
With the modified firmware, you can, of course, simply ignore this message and send with the full power. So if the network tells all the other phones use, let's say, 1.5 watt of power, I can still send with 2 watt because I don't care. And then I'm effectively jamming and no other one would come through.
I I see. Is there an additional channel for emergency calls? Or if this
It's
cell
the
is
same.
jammed completely by this kind of attack, no calls at all are possible anymore?
There is also, it's also no longer possible to make an emergency call. One of the reasons which can be sent for a channel request is also, I want to have an emergency call.
Yeah.
Of course, I can send the cause with this attack. Currently, I'm just telling the network with different random numbers, I want to make a call, but it's of course also possible to just say, I want to make emergency calls all the time. If it prioritizes those emergency calls, then I send a flooding attack with emergency call reasons, and then again, I get all the channels.
So it's basically a stupid idea if I don't want to kill people.
Yeah. That's of course also the reason why it should not be just for fun tried in the public, of course, because you make the system unusable, or at least the cell.
I have actually two questions. The first one I just want to ask for the record because I don't expect an answer. Have you tried that in the wild with a major self-network? Okay.
Really not. I haven't tried it in the wild. I have tried it with OpenBSC in a own controlled environment and in a lab environment with the allowance of the operator who is working this lab environment.
And another question is, would you expect major cell phone network providers to have any kind of detection possibility for such a thing?
I guess so, that they can detect it. They, of course, observe how the network, how the cells are loaded. So they see how many calls are going on. If this happens, they will get some indication that the cell is really allocated completely. But what should they do at this point? They can try to change the configuration of the cell and tell in some way the phones on the net on this cell switch to other cells and try it there. But of course this attack is easily scalable. Just take more phones, position more people at different places, and yeah, it's easy.
Which leads to my last question. Have you received any kind of feedback from the cell phone network providers towards your attack if you tell them that's possible and how to do it and how easy it is?
Not yet. I think this attack is known for, let's say, 2 or 3 years. They already know that this is possible, but they also know that there is not much they can do. It's rather similar to A51. A51 can be cracked, they know it, but what to do?
Thank you.
Any more questions? Okay.
One last talk.
Sorry.
Are running calls affected of the
Sorry?
attack? Are running calls affected of the
No,
attack?
no, running calls are not affected. If you are making a call or if you have, let's say, a data connection established, running, they will not be disturbed or interrupted. They still continue. But if you're doing a handover, let's, for example, imagine you are moving in a train from one cell to another. If you switch from one cell to another, the handover process also needs a channel. So at this point, you will be interrupted because you don't get access to the next cell. Okay.
In your slides, you said that this could be used to basically jam an IMSI catcher.
Yes.
Couldn't this not also be used to get exactly the opposite result? Basically to provide a way for an IMSI catcher to catch phones, even so they are not the IMSI catcher is not the most powerful cell in the area. By jamming the most powerful cell.
It depends a little bit on the software. Currently, when I experimented with this denial of service attack, the test phones I had did not try to switch to something else. They still tried to get access. They just say, network not available, but they continue to try on this network because it's the strongest one. I don't know if there are phone implementations which actually switch at some point to a different cell. If they detect, okay, I have tried it for 4 or 5 times, did not get access, and now let's try another cell. If this would happen, then of course it could be used the way you explained it.
Okay, thanks.
And what do you think about the GSM data cards that are currently available? Are there any use for your type of approach? For example, Qualcomm chipsets and similar?
Currently, Yeah, if you want to implement it on a different type of phone, or is this what?
Yes.
Okay. I think if someone knows even the phone firmware very well or reverse engineers it, I think it could be possible to find places where this attack can be implemented. Imagine a phone which uses also the Texas Instruments Calypso chipset. One problem here is this chipset is already out of production. It's no longer used in current phones. But imagine you have a phone with the same chipset. Usually the GSM stack comes from only a few vendors. So the code, even the binary, would look very similar of the binary generated by the source code. If you reverse engineer it, you can find the places and probably patch the binary and implement it on a phone where you don't have the source code. Of course, someone who has programmed the firmware, let's say someone knows the details or some details, for example, about the iPhone. The iPhone, as far as I'm aware, is attacked over the baseband chip to jailbreak it. So they are already inside the baseband chip where GSM is running. If someone knows the iPhone firmware quite well, it could be possible not just to jailbreak it, but also implement a task which runs this denial of service attack. It's just a matter of time, how much time you want to use for reverse engineering your firmware. Okay.
But just one question, isn't it true that normal calls are terminated if you request an emergency channel?
I have not made this experience yet in our test environment. It was a real cell. I could imagine that it is possible to configure the cell this way. But so they can, so for example, the base station controller could say, okay, let's release all the other calls. We have an emergency request. But if we are jamming, this emergency request will not come through.
No, but if you jam with an emergency request, you would be able to terminate other calls that way.
Yeah, if we find another provider who wants to test it in a controlled environment, we are happy to do so. So we would luckily try it out. But if we try it out in the wild, let's imagine we would do that. We would not see what happens actually. We can try with a second phone and see, okay, now I come through, now I don't come through. But to really understand what is going on behind, we need the help of the operator who says, okay, we provide the logs to you and you can see what is going on. So then we can try it out. We are happy to do this. If someone knows someone who wants to try it, okay, fine, we are there.
Okay, thank you for your patience. Give a big applause to the speakers.
Thank you.